So welcome everybody to the seminar today. And today we will have Julian Sonner, who will be talking about his recent work on modeling chaotic CFTs and also semi-classical 3D gravity. So over to you, Julian.
All right. Hi, everybody. Thank you, Ian, for the introduction. Thank you for inviting me to speak about this work. So I will immediately start with some introduction and background. Well, yes, I think I will acknowledge my collaborators when we get a little bit further. So then we'll do it. So the motivation I'm giving here is very broad. I will give some more specific motivation as we go on. So let's say ultimately, indeed, we are undertaking this kind of study because we are interested in gravity. And in gravity, the age-old question is how we understand macroscopic phenomena such as black holes and perhaps even more future-looking, something like cosmological aspects of space-time at the microscopic level. And how do we reconcile, in some sense, a consistent microscopic description with what we believe to be true at a macroscopic level? And so one concrete starting off point at the level of black holes is indeed this issue that we have a semi-classical formula for the black hole entropy, which is the Bekenstein-Hawking formula, and which basically tells us that the entropy of the black hole is proportional to the finite area of the compact horizon in Planck units. Now, there is, of course, a lot of progress and wonderful work on sort of enumerating the number of states that statistically contribute to this entropy. So there's sort of microscopic straight counting in many examples, and even recently there has been more and more impressive progress on this. But actually, the kind of questions that we're going to discuss today, they go a little bit beyond, say, the idea of merely counting the number of states, but in fact, what we want to understand is really how do these states arrange themselves? In other words, what is actually the spectrum itself? How do the spectrum of, in particular, black hole states arrange themselves? And so this is what I mean by this question: what is the microstructure of the black hole Hilbert space? So in other words, the states that make up predominantly this Bekenstein-Hawking entropy. And moreover, also, I will sort of comment on what we learn about semi-classical gravity from this, in particular regarding the nature of these recently sort of very famous connected contributions, such as wormholes, that we find as contributions in semi-classical gravitational theories. So that's a very broad motivation. But actually, as I said, there will be much more specific things that I want to discuss. And those are indeed based on 3 papers mostly, although I think the conceptual framework, there will be more papers that I could mention here. But the ones that I consider more in detail are ones that I wrote recently with Dan Jafris, David Kolchmeyer, Bauer, Mohamed Sanoff. And actually, a sort of distilled version of the ideas is about to appear in PRX. And more recent work with Dan again, and with Alex Berlin, Jan de Boer, and Franjan Nayak. And of course, a lot of the things that I say here, I owe a lot to my collaborators. It was it's really a very fruitful collaboration that I'm very happy about. So I will try and tell you a little bit why we're going to think about sort of averaging over matrices, or later on even tensors. And I will sort of give you an overview how they have come up in the past in the context of quantum chaos and quantum gravity. And we will sort of make connection to this, but in novel ways. Then I will go straight into new material, namely this thing which we called here the ETH matrix model, ETH standing for eigenstate normalization hypothesis, and I will, of course, explain what I mean. And that has an immediate gravitational application, which was actually the first motivation to think about it, which is to 2-dimensional JT gravity plus matter. And then in an attempt to generalize this to higher dimensional gravity, I will tell you about, in fact, how to think about the statistics of the crossing equation, and in fact, in some sense, averaging over chaotic CFTs. And we will distill that into a concrete tensor model for chaotic CFT, which also shows properties of three-dimensional gravity. So this will be sort of lifting what happened to the JT and matter one dimension higher. Now, I should say maybe from the outset, it's important. I will mostly talk about two-dimensional and three-dimensional gravity, but what I'm saying about the statistics of crossing and chaotic CFTs is actually also applicable in higher dimensions. Whether there is a useful gravitational application beyond 3 dimensions, I don't know. Okay, so this is maybe some things that you have heard from others or even from me in some context, but I still think it's worth reminding ourselves of it. So how do matrices and matrix models come up in the context of quantum chaos? So actually, one of the best ways of thinking about quantum chaotic systems is to think about, if you want, the most intrinsic property of a quantum system, namely its spectrum. I already mentioned the spectrum. Again, here I'm talking about the spectrum of energy eigenstates of the Hamiltonian. So there are, of course, other competing notions how to think about chaos. You're probably aware of things like out-of-time order correlation functions and Lyapunov exponents, and I will make some comments later. But the most intrinsic way of talking about it is to, in my opinion, focus on those things which are universal to every quantum system, and talking about the spectrum is certainly a universal notion. So in this context, it is understood that if you look at the Hamiltonian of a system that is chaotic, then the spectral properties in a statistical sense, you can describe by, instead of thinking about that fixed Hamiltonian, so for example, the Hamiltonian of a complicated nucleus, or in our case, of a gravitational theory, you can replace this Hamiltonian by actually an average over matrices, which sort of stand in for this original Hamiltonian. And this is RMT here stands for random matrix theory. So you can characterize the spectrum of a given physical system by instead thinking about matrix integrals. And this is the idea that was first formulated by Wigner and much developed by Dyson and Mehta. So how does this work? Well,
something.
Yeah.
So for which class of observables this replacement is good?
Well, one class of observables I'm going to talk about now, and then actually part of this ETH matrix model is actually to grow the class of observables that you can fruitfully describe in this way. Okay, so one class of observables is precisely the idea of the spectrum itself, but in what sense? So one example is the two-level spectral correlation function. So let's say, you want to know, for example, how are levels distributed across the spectrum, and you want to know, for example, what is the likely distance between two levels? You take two neighboring levels and you ask what is the distance between them. Well, you can ask this question about your favorite chaotic quantum system, and I want you to focus here on the left side on this sort of histogram type curve. So what is this? It means that you take an energy level somewhere in the spectrum, and you ask how far away is the neighboring energy level. And you do this all across the spectrum, and you sample all of the level gaps in the whole spectrum, and then you make a histogram, which is saying, for example, here, there's only a few levels that are very close to each other, and then there are some more, I'm binning this. This is a histogram, okay? So this is some sort of finite resolution sampling of the spectrum. And what this curve is saying, this is supposed to be representing, say, a nucleus, that the frequentist likelihood to find two levels that are almost degenerate is very low, while the frequentist likelihood to have two levels that are sort of a mean distance apart from each other is pretty high, and then it starts going down again. So this is one piece of information that you can ask about the statistics of the spectrum. And Wigner's idea, which is basically vindicated, was that this histogram, if you take some sort of continuum limit, is actually described by the exact distribution that you get by instead not taking your quantum system, but averaging over all Hamiltonians that are consistent with the symmetries shared by your quantum system. Okay, so in that sense, one observable ion is the two-level correlation function. Okay, and I should say that S here is the spacing between the two levels in particularly convenient units, those units being the average level spacing. Okay, so on average, levels are approximately 1s apart, but in fact, some of them are very close, but it's few of them. Okay, and some of them are very far, but it's also few again. And this curve here is a mathematically known function which can be derived by averaging over matrices. This was Wigner's idea, and as I said, it is basically vindicated. Now, other observables in the same spirit ion would be any n-level correlation function, so 3-level correlation function, 4-level correlation function, and so on. So more and more fine-grained information about the actual distribution of levels. Okay, but in the sense that you have to sample over the spectrum. Okay, now, so everything you might want to know about energy levels can be, from this original idea of RMT, can be characterized. Now, two aspects that I do want to emphasize is that it is indeed very unlikely to find two levels right on top of each other. So that's a property of chaotic systems. It says that chaotic systems don't like to have levels next to each other. And one often speaks of level repulsion. Levels, don't want to be on top of each other. And just to contrast that with a system that's not chaotic, that would be the dashed line here. That's a distribution which is not Wigner's distribution, it's actually just a Poisson distribution. And this has a substantial probability that levels are close to each other. Okay, so that's, for example, a big difference. Now, okay, I could go on forever about this. There's a beautiful theory, but I want to go forward a bit. I want just to point out that this is energy resolved if you want. And you can instead go and time resolve it by sort of Fourier transforming the two-level correlation function. And that's what people have talked about a lot in our community. This is what the spectral form factor is. The spectral form factor is a Fourier transform of the two-level correlation function. And what that means is that the longer this spectral form factor I let the time pass, the more it gets sensitive to very tiny UV features of the level spectrum, because you see the difference in energies are Fourier conjugate to time. So smaller and smaller energy differences contribute at later and later times. And once you get to this characteristic energy difference where this curve here is valid, then the signal of an actual system, the black signal, will actually converge again to Wigner's prediction. Okay, and the characteristic time at which this happens is known as the Thouless time. And then there are some other characteristic times which we don't need to talk about now, but I can just mention it. This is known as the Heisenberg time, or also the Plateau time. So the point is, matrix models describe the spectrum of quantum chaotic systems in the sense that I said. Quantum chaotic Hamiltonians show RMT statistics. And typically around Wigner and Dyson and Meta, this statistics is supposed to be Gaussian. And this is something that we will revisit. Now, other probes you might want to talk about. So for example, correlation functions of actual operators. Now here, people typically don't talk about matrix models, at least not in a direct sense. They talk about this so-called eigenstate thermalization hypothesis, or ETH. And this I have formulated here. This also, in some sense, in an independent way, attempts to answer the question, how do chaotic, i.e. thermalizing systems, how do I characterize them? And if you're willing to think about operators, then this turns out to be very successful. One just assumes, or attempts to prove, depending on one's, I guess, theoretical foundations, that the matrix elements in energy eigenstates, so I and J are energy eigenstates of non-extensive operators O, take a very specific form. There is some smooth function of the average energy of I and J on the diagonal, but what's more interesting for our discussion today is what's off the diagonal. So there is there is an entropy, which you can take as a microcanonical entropy at this energy E bar. There is a function which is a smooth function of the energies Ei and Ej. And then there is a Gaussian random matrix Rij, which sort of governs the fluctuation that are on the off diagonal of these operator matrix elements. Now, the success of this kind of ansatz, at this point it's an ansatz, is that it implies the thermalization at long timescales of non-extensive operators. Okay, and again, I say that this works if Rij is a random matrix, and typically people take it to have a Gaussian distribution, which we will revisit. Okay, so this fact that this Gaussianity here has to be revisited was also pointed out by other authors, and I'm naming some of them here. But more to the point, what we would like to do is to basically fit these two different observables, namely spectral and operator matrix elements, into a joint framework. That's sort of step one of what I want to tell you about. And that is what we have called the ETH matrix model. So there will be a matrix model type, a matrix integral type theory, which incorporates both the spectral information and the information about operators. And now, Ian, you can, for example, extend the kind of probes that you can talk about very widely, because basically any operator correlation function you can now start investigating, not just spectral properties.
So the main point would be that the measure would be independent of which operator you're looking at, and or which specific observable you're looking at.
There are parts of the measure which can be independently determined, but notice that even in the ETH ansatz, there is this function f, which I said is a smooth function. In fact, even this function O here, right? I didn't actually tell you what they are. They do depend on the theory, and they in principle can also depend on the operator. But you will see that in cases that we are interested in, so in principle, we're going to develop something which depends on a hierarchy of undetermined functions, but you can still use it to predict things like thermalization, okay? However, if you want to be more specific about particular models, you will need to find a way of determining this hierarchy of functions. And we also supply a way for theories of interest in holographic duality of determining these functions. And I will explain how that works. Okay.
Okay.
So this remark here, okay, I've given talks about this, but I do still want to mention it, that there is sort of some way you might ask, why does this random matrix idea actually work, and why can we describe operator statistics with this kind of ansatz? And one way of doing it, especially in the many-body business, was recently emphasized by myself and Alex Altman, but goes back to old work of Wegener and Yefetov. You can actually think of this as a manifestation of a very universal symmetry breaking principle, which I'm just illustrating here with some supergroup symmetry breaking. We don't need to really talk about the details here, but it's universal in the same sense that Goldstone effective field theories are universal, and you can understand the emergence of random matrix theory for chaotic systems in this context. So it doesn't just come out of thin air, even though in the beginning, Wegener really seemed to have pulled it out of thin air. It was just a really fantastic guess. By the way, on my side of the screen, there is some pop-up window show active speaker video in the way of some equations. Can you see all equations?
Yeah, we can see everything. No
okay,
problem.
good.
Yeah. No pop-ups.
So the last sort of piece of background I want to give is, so now we have thought about the emergence or the appearance of random matrices for quantum chaotic systems. However, the same kind of mathematical structure, namely integrals over, say, Hermitian matrices with measure that we can specify that will give us some sort of potential, they came up in a seemingly completely different context, namely, in this case, in low-dimensional, two-dimensional gravity. And the idea here is the following. The idea is that, let's look at the formulae. Let's say you wanted to construct the path integral over two-dimensional universes with some specified boundary conditions. For example, I've illustrated here a universe with one boundary. So it's a universe, but it ends on a boundary, this circle. Then one way of doing it is actually that if you zoom in, you sort of find a discrete version of that space-time where you have sort of discretized the metric curvature, and you have essentially triangulated your surface. This triangulation of a 2D surface can actually, the combinatorics of these triangulations is actually equivalent to the combinatorics of certain matrix integrals that have nonlinear potentials. So the double lines here are exactly the 't Hooft double lines of a quartic matrix model. It has a trivalent vertex. And if you look at the dual graph, which is the solid lines, you see that this gives a triangulation locally of the surface. Okay, and the beautiful idea of these authors was that by taking the integral over all possible such diagrams, so all possible triangulations, in this case, all possible 't Hooft diagrams of some matrix model, and taking a continuum limit, I can construct the two-dimensional path integral, and not just on surfaces or universes, if you want, of given topology, but it has baked in through this 't Hooft topology counting of matrix model graphs, also a topological expansion. So you can have a universe which has, in this case, the trivial topology that's consistent with having one boundary. You can also have one that sort of, spits out a baby universe and an anti-baby universe and absorbs them again. So in other words, it has a handle and many other handles. And so the random matrix theory here gives you a discrete triangulation of these two-dimensional universes, and the continuum gravity path integral emerges from a limit, which basically makes this mesh infinitely fine, and the area per triangle scale at the same time, so that you get a finite continuum limit. Now, these two things were actually thought to be completely different points of views on matrix integrals. And what one of the main points that I'm making today is that, in fact, in many interesting cases, they're exactly one and the same thing. So now the more specific motivating questions, I gave sort of the big motivating questions at the beginning. Here are some more specific ones. So in other words, what is the Wigner ensemble for a holographic conformal field theory? Okay, so we have strong reason to believe that holographic CFTs are chaotic systems, but they are very special chaotic systems. Can we say something about how their sort of random matrix type description should work? And I will answer that question. 2, can we establish in controlled examples a connection to gravity? Yes, and I will answer that question. And 3, more insight about gravity as an ensemble of quantum theories. That is maybe more subject of discussion. But will be interesting to revisit that question, given what we learn in 1 and 2. So good. So this is maybe a good time to pause for questions.
Yeah, just one naive question is, suppose maybe you're focusing on 2D CFTs, but in higher dimensional, we know that there is something like a universal sector in holography where you have just pure solutions of pure gravity. Yeah. So is there could be some understanding from such generally can emerge?
Yeah, so first of all, I mean, we believe we have a model that works in 3 dimensions. So not 2-dimensional gravity, but 3-dimensional gravity. But that definitely uses the fact, so that is not a generic chaotic CFT. That's a chaotic CFT that has a particular kind of spectrum and so on. Okay, that is compatible with it being dual to pure gravity. And that gives a particularly nice version of our model of a chaotic CFT, which I haven't yet explained, but I will. Now, higher than 3 dimensions is actually, to me, an open question. But I think, as you already allude, the fact that there is this universal sector in holography must play a crucial role. But maybe we can revisit it in the discussion after I've actually explained how we do this construction.
Okay.
So let's go to the ETH matrix model. So this is, if you want, for now, some work that could be seen as a contribution to statistical mechanics, and how it relates to gravity will become, I hope, evident only later, or well, will become evident later. So the first order of business would be that we need to revisit this assumption that the Rij matrix is a Gaussian matrix. In fact, it was appreciated over the recent sort of 3-4 years that it cannot be so. And probably, I mean, to be fair, this is something that in that community, the statistical physics community was known, but it was not widely reported or used. So the way that we realized that there should be some correction to this Gaussian is that we actually tried to compute something like an out-of-time order correlation function. Just a 4-point function is actually enough. And what you find is that the ansatz, this ETH ansatz, if you just plug it straightforwardly into the 4-point function, it actually completely fails to capture Lyapunov type chaos. And the reason is simple to explain. The reason is that actually that's the formula that I'm writing here at the bottom, is that if the statistics is Gaussian only, then you can calculate everything with Wick contractions. But with Wick contractions, you never get a non-trivial Lyapunov exponent. So in order to characterize a non-trivial Lyapunov exponent, you have to have a connected contribution in the statistics of the R matrix that has 4 R matrices. So a connected 4-point moment. And it has to be very highly suppressed. I will return to the formula in a second, because we can say more generally that actually, if you, for example, just calculate a 4-point function, you can convince yourself that that 4-point function using this naive ETH ansatz will fail to satisfy crossing invariance. Basically, because the third Wick contraction that would give you a crossing invariant 4-point function is actually subleading. And you need to reintroduce something that can contribute at order 1 to the 4-point function, which restores crossing. And it turns out that is exactly of the same structural form as this 4th connected moment of the R's. So in other words, there are many observables, this is this ... that you can convince yourself easily are simply not captured by this Gaussian assumption in ETH. And there needs to be a full hierarchy of non-Gaussianities, of which I'm showing you the first leading one. So there is a G4, which now depends on 4 energies. I want you to remember the F, which depended on 2 energies. There's a very similar thing. And this guy is very highly suppressed, seemingly, with 3 factors of the size of the Hilbert space, e to the -3 times the microcanonical entropy. However, actually, it is not suppressed at the level of correlation functions, because any correlation function will contain this contribution with 3 integrals over the Hilbert space. And that's exactly compensated by e to the -3s. So it actually contributes order 1 to things like out-of-time order correlation functions. And so in fact, from a ETH point of view, and there was also a paper by Murthy and Srednicki on this, the Lyapunov exponent from an ETH perspective is precisely encoded in this G4 here. This G4 is something like this F that I had here. I could have written it G2. Okay, so we need to de-Gauss ETH, but we can do more. What we can do more is, so we can say that there should be some sort of non-trivial, non-Gaussian statistics. And I didn't write the equation here, but there should be a Gn with a suppression factor of n-1 instead of 3. Okay, so there's a whole hierarchy of functions. But the best way of organizing this hierarchy is actually by writing, yet again, a matrix model. And this matrix model is now not going to be a matrix model that has just one or the other matrix. It basically now has both the H-type matrix, which talks about the spectrum, and the R-type matrix, which talks about the operator. And by some sort of simplification of the notation, I'm calling the matrix that I'm integrating over. I could have called it R, but I'm calling it O to remind ourselves that it has to do with this operator. So I can arrange both the level statistics and the operator matrix element statistics as a matrix integral, this time over 2 matrices with a single trace potential that depends on the H matrix and the O matrix. And what we can do is we can characterize what this potential should be in the eigenbasis of one or the other operators. But from the ETH point of view, I was giving here the matrix elements of the operators in the eigenbasis of the Hamiltonian. That's what I and J are. It is most natural to write it in the eigenbasis of the Hamiltonian. And in this case, it will take this rho. So there will be the potential for the eigenvalues, which determines the spectral density and its statistics. Then there is, if you want, the e to the s I'm calling it e to s0 here for historical reasons. I'm sorry, this should be e to the s. This will be the Gaussian term. So this actually determines the little f 2-point function. It's not exactly equal to, that's why I'm writing it differently, but it determines it. So this is like a quadratic term for O, but that would not be good enough, as we said. That would violate, for example, crossing. So we add actually.
I'm really sorry to interrupt, but sorry to interrupt this. But what is this Z supposed to mean? What is this?
Well, in principle, this is just a partition function, but of course, we think of it as a generating function of either spectral correlators or O correlators. So, for example, you could put a source for energies, and then, for example, calculate expectation values of rho of E1 times rho of E2 times rho of E3. Okay. Or you could introduce sources for the O operator, and you could start calculating, for example, out of time order correlation functions.
Oh, okay, I see. And this is essentially vacuum expectation values of average.
No, actually, no. What we think of is, so first of all, so these are expectation values in the matrix model. Here, they are just indeed expectation values of the matrix model. But they don't relate to vacuum quantities of the chaotic underlying system. In fact, they allow you, for example, to look at finite temperature expectation values. And in particular, those are the ones which you would expect to thermalize. So those are the ones which you would like to compute. But moreover, if you talk about the spectrum, it also just allows you to calculate things like what is the correlation function between energy level E1 and energy level E4, for example. I don't know if you would call that vacuum correlation function. Or call it,
it's a
statistical.
I understand this.
About the spectrum.
I'm confused also about your like where is the time enters here? For example, this OTOC is time dependent, but there is
you will have to have insertions of the Hamiltonian e to the I. For example, let's have complex time e to the tau times h, right? You would put something like trace up e to the tau h operator e to the minus tau h of the operator. Then the h gets averaged over as well, right? But it still has a time insertion point tau, which you can think of complex. You could then continue it to real time, and you can ask about real-time correlation functions in that sense. Right? So this thing does also, that's actually important about this ETH matrix model. It has both the H built in and the O. And then if you calculate a correlation function, well, you assemble your correlation function. For example, you could assemble it with insertions of exponentials of the Hamiltonian. You would call that time evolution. But the way that the matrix model calculates it for you is that you average also over H. And the reason that the average over H is this quantum chaos reason that I actually told you before, that in quantum chaotic systems, this is a good a way of thinking about time evolution.
Okay, thanks.
So, okay, so finishing up for the CTH matrix model. The potential determines the average spectral density, the average correlation of the spectrum, and so on, higher moments. So it gives connected energy correlations. It also gives the disconnected part, but in particular gives connected energy correlations, which is interesting. The function f and this hierarchy of GNs gives you the non-Gaussianities of operator statistics. But I already alluded to this, like in the standard way of thinking about ETH, these are free functions, and the question is how to determine them. Okay? And actually that is a lot of where our technology goes into actually in interesting cases determine what they are. So I want to emphasize that from a statistical physics perspective, ETH is kind of like, it is predictive, but only to a certain point, because it contains these free functions. And if you want to really apply it to a specific system, then you would have to determine what these free functions are. But even without knowing these free functions, you can already say a lot about, does a system thermalize? What are sort of the universal properties of thermalization, and so on and so forth. And in the same sense, in the ETH matrix model, you can say, You can make statements of this kind. So that's already interesting, but our actual goal is to use it to describe specific systems, such as JT gravity plus matter, or chaotic CFTs that are dual to 3D gravity. And then we need to find a way of determining these functions. And this is what I will try to explain next. Okay, so in particular, how do we determine them? Well, we need to actually input more knowledge. And this is even in information theoretic terms, you can think of it that way. So I will explain that later. So one source of such knowledge would be to go this route of the effective field theory of quantum chaos. And actually, with Pranjal and with Alex Altland and with Dima Bagratz and also with Manuel Vielma, we actually wrote a couple of papers on this. I could have cited them here. And if you're interested, I can give you those references. But more to the point of the more recent work, you can determine these non-Gaussianities by imposing constraints. But these constraints are actually of a general kind. For example,
can I ask the question?
Yeah, can I finish the sentence and then yes. So for example, something about modular crossing in 2D CFTs and channel duality in CFTs. Yes, please. There was a question, right?
Yes, sorry. So I was wondering that in this, I think I was wondering about the non-universal sector of the, if I think of a many-body model and it has also non-universal sector. So this ETH matrix model will be strictly valid only after the Thouless time, right? Or how would one incorporate non-universal?
No, I would, yes. So I would not fully agree with that. I would say that in a completely generic system, I can probably only hope to describe post-Thouless time physics. But for reasons that go actually into this discussion that we should have about the nature of semi-classical gravity, in examples like JT and also in three-dimensional gravity, it turns out that the applicability of these matrix descriptions is actually at all times. So I understand that you can push them, to earlier times than the Thouless time because you're actually giving more information, you're reducing the entropy, and you learn more about fine-grained features that contribute before the Thouless time. But the fact that there are some models where it seems to be true at all times is something that I don't yet have a good understanding why this is the case. But in those gravity models, in particular, it's just true that JT and JT plus matter are described by these matrix models at all time scales. Okay. And this may well also be true for three-dimensional gravity if the theory that we write down is correct.
Okay, thank you.
But as a general statement about where this is situated in the theory of quantum chaotic systems, your point is absolutely correct. Okay, so so now let's talk about approximate CFTs. Okay, I should have said I didn't want to go into the details because that would have taken me the remainder of the seminar. I've tried to do this before and it hasn't worked out so well, but we worked out the details of how to apply this to JT gravity plus matter, and you can read it in this paper and actually a much longer companion paper. But I want to talk about the more recent paper, and I think it also streamlines a little bit the kind of developments that we do. So I would like to talk about chaotic CFTs. But in order to talk about chaotic CFTs, I will first have to tell you about what we call approximate CFTs. So the point is, we would like to develop something like appropriate random ensembles for chaotic conformal field theories. And of course, there have been other groups over the years that have been thinking about this. Yes, I'm acknowledging some of this work. But I think our more recent perspective is somewhat different from what has been said. So let us think about the idea of developing such an ETH matrix model for chaotic conformal field theories. So one might say that it's, you know, you don't expect this sort of straightforward Wigner universality, which actually in modern parlance is called Altland-Zinbar universality, that you have for many-body quantum systems for things like conformally invariant field theories. The reason is simply that there's too much local constraints that come from those symmetries to, you know, be able to just define, you know, the symmetry classes like this. But in fact, the situation seems to be, the evidence now is that the situation is as good as one could have hoped for, in the sense that once you take into account the constraints of conformal symmetry, the sort of invariant subunits that are left still behave like Altland-Zinbar type RMTs. So what we need to do is we need to basically sew together sectors of random matrices in such a way that they respect the CFT constraints. Okay, so this is what we do. And the most natural approach then would be, or it is at least in my opinion, what is a CFT? Well, a CFT, well, you know, we could start with some Lagrangian and calculate a whole bunch of diagrams and find that beta functions vanish, and we could work on this level. But actually it has turned out to be very powerful to instead think about giving a set of data. You know, this is of course the sort of bootstrap approach. This set of data will be the set of all of the primary operators that you have, here denoted by their conformal dimensions delta I and their spins ji, and then the 3-point functions Cij, the so-called OPE coefficients. But then, of course, it's not true that any list of delta I and ji's and Cij will give you a consistent CFT. In fact, these data define a CFT only if they satisfy consistency conditions, namely the bootstrap conditions. So, you know, you have to have like a convergent OPE in some channel, and you have to have certain crossing constraints that the endpoint functions need to satisfy. So if we just average over this data, which might be, you know, the first idea, namely the deltas, the j's, and theCijks, without taking into account that there are some consistency conditions, you know, we're not averaging over CFTs. We're averaging over the data of CFTs. And this is what we will want to do, not with a completely free measure, by the way. We will have some measure, but in principle, we're averaging over data. And so we need to think a bit more about what are actually the elements that we average over. They're certainly not going to be all CFTs. So that's where this notion of approximate CFT comes in. So let me say a couple of words about this. So this definition of approximate CFT is that it is the set of data, delta, J, and C, which approximately satisfies CFT constraints. And approximately satisfy CFT constraints for us means that we impose the CFT constraints only for a subset of what we might call light operators. This is this O restricted. Light operators is actually motivated by a future application to gravity and has to do with, you know, things that, you know, like things that a supergravity observer can have access to. But you can in general just say in a CFT, you take a subset of operators of conformal dimension up to some delta max, which I'm calling here delta max, and that's your set of light operators, just a definition. Moreover, and this is maybe a little bit counterintuitive when you first see it, but these constraints, even on the restricted set of operators, are only imposed up to some tolerance parameter T. And I want you to think of T morally like e to the minus entropy. Okay, this will have to do in specific examples with this entropic suppression, but in principle, you could just say it's some small parameter, which I take as part of the definition of this approximate CFT. But again, once we have, you know, semi-classical gravity in mind, it will be something like e to the minus entropy. So like something like e to the minus n squared in n equals to 4. Now, so let me say a couple of words. Why are they only imposed up to a tolerance parameter T? Well, that's because, let's say, we certainly impose these constraints for the restricted set of operators, but I have said nothing about the other operators. And in fact, the point is that we do not want to impose this for the other operators. But then because the other operators can actually propagate in intermediate states, even in correlation functions of this restricted set of operators, it would be inconsistent to claim that the restricted operators satisfy exactly crossing. Okay, their crossing, for example, would be polluted by the violations of the operators that are not in the set or restricted. So it would not be mutually consistent. So for consistency of the whole construction, you need to both have a restricted set of operators and you need to have some tolerance parameter. Okay.
And what is this?
Now, this
capital, what is the definition of this capital S generally? Is this some arbitrary parameter or it is
the capital what?
The S, e to the power minus S, the S.
Yeah, so as I said, morally, this is like the entropy, but the entropy, of course, you should think of just telling you something that scales extensively. So for example, it would be proportional to e to the minus n or something like that.
It's some kind of, so
yeah, like 1 over g newtons, for example.
Has to put a central charge or something of the system.
Yeah. Well, no, I would say it's a property of the theory. So for example, in the CFT4 ADS5, it would be e to the minus n, where n is the rank of the gauge group.
Mm-hmm.
So think of it as e to the minus 1 over g Newton in a holographic CFT.
Okay.
So equivalently, we can see the first 2 points as being imposing a restriction on the maximum number of insertions you can have in a correlation function, the maximum individual conformal dimension that an operator can carry, and you have to actually also restrict Lorentzian cross ratio space. And then if you go to 2D CFTs, for example, if you get more specific, you might also need to restrict the genus of the surface that you're allowed to consider. So I'm leaving it open here, but in general, it's these 3 parameters. As I alluded to, in principle, this allows large violations of the CFT constraints, but in a way that is carefully correlated across the spectrum. And we'll see how to do this careful correlation. This is basically the imprint of conformal invariance. Okay. Now, another way of thinking about this is that we're only imposing the bootstrap constraints approximately. And therefore, the expectation would be that instead of ending up on specific theories, once you impose all the constraints, you still leave open some islands, and those islands are precisely this parameter space that you can average over. Now, this sounds abstract. So to reassure ourselves, we constructed some simple example of what such an approximate CFT would be. So the simplest example that we could come up with, which also illustrates, by the way, one of the subtleties, is the following. So let's take a true CFT, so a set of CFT data that satisfies all the bootstrap constraints. And let's take a single operator O0 and let's just shift its conformal dimension. So you've taken a CFT, and if epsilon is small, then in some sense you'd expect that this thing is actually close to the original CFT. However, that is not true, because if O is a member of O restricted, so where you want to impose the constraints of crossing, you can convince yourself that the correlation functions of O violate crossing arbitrarily. Okay, so in other words, you cannot just shift the conformal dimension of one of the operators that is in your restricted set. You have to do it of one of these heavy operators that you don't specify the constraints for. And why is that? Okay, it's actually easy to see, right? Because correlation functions will typically have power law singularities 1 over, cross ratio to the power of conformal dimensions. And shifting this conformal dimension by epsilon, it can still lead to huge differences because it's basically singular with epsilon. So it'll give you logarithmic singularities in cross ratio. And so you can always find some cross ratio that makes the violation arbitrarily large, no matter how small epsilon. So this doesn't work. Okay, so this naive prescription just won't work. Okay, this is what I'm saying here. Okay, basically, you have violations that are logarithmic. They're not uniformly suppressed in epsilon. So there's no choice of epsilon, which makes this uniformly small. But in fact, what we show, and it's not such a complicated calculation, but yes, in interest of time, I decided to refer you to the paper, that these kinds of violations can be counterbalanced. So in the simplest way to counterbalance it, you would just say, let's shift the second operator by a different epsilon in such a way that their shifts are correlated with their mutual conformal dimensions to make the coefficient of anything that depends logarithmically on the cross ratio vanish. And it turns out that, some calculation shows that that can be done. So you cannot shift one operator by itself, but you can shift, for example, two operators in a correlated way. And you can, of course, generalize that to n operators. And the reason...
Julian, isn't it kind of obvious that this should be possible? Because ultimately, these parameters are not isolated. I mean, the set of consistent CFTs are not isolated. So there has to be any small variation which will make it consistent. There should exist some small variations that should make it consistent.
I'm not sure I understand your argument. So what is not isolated?
I mean, suppose we take a particular example of a CFT with this CFT
No,
data.
but I think you're saying that there should be a marginal deformation, but there isn't in typical CFTs.
Yes.
So if there's a marginal deformation, then we could just average over the marginal deformation. But in fact, this is not the generic case. And that is, I thank you for raising that point. That is actually one of the motivations why we need to go to this approximate CFT, because if you don't have marginal deformations, what are you going to average over? Of course, if there is a marginal deformation, then you can do it, but that would not be this construction. Then you would actually be averaging over exact CFTs, which is just a special case of averaging over approximate CFTs.
I understand what you're saying, but suppose if you have a very large central charge, I would expect that there has to be, I mean, generally some kind of family of solution up to 1/c or something that should work, I mean, intuitively, there should be some kind of they would be effectively continuous. The discreteness should be over 1/c kind of.
Well, that's an interesting point. Maybe we can discuss it later, but this definition here works for any CFT or any sort of list of data. There is no assumption of large central charge or anything. So what we're proposing here is more generic. It's true that maybe in some more restricted set of circumstances, you can think about averaging over exact CFTs. And in fact, people have done so, for example, by averaging over this moduli space, the Rhine moduli space of CFTs. Okay, but certainly our approach is meant to be more generic for generic CFTs.
Okay.
Okay, and so the point is that with this procedure, you start with a CFT, you deform it in a correlated fashion, and of course it's correlated because the conformal constraints basically correlate things across the spectrum. So we're just kind of in a pedestrian way implementing CFT constraints. But crucially, it allows us to produce violations of crossing in the restricted set of operators, which is uniformly bounded by epsilon in cross ratio space. And so now you can just say that, for a small epsilon, you can say I have a CFT I have a structure that is almost a CFT, therefore approximately CFT. So the motivation from holography is that, you want to think of the restricted set of operators to be somehow dual to the observables that a semi-classical observer will have access to. But as we just discussed, certainly our definition is also made in such a way that it applies to CFTs that are not necessarily related to holography. But from the holographic point of view, I want to make one more comment this audience will probably understand very well. Because, if you say these correlation functions are dual to like supergravity observables, then of course you immediately see that they're only determined by definition to perturbative order in the 1/n expansion, which is like, okay, I called it this, e to the minus s expansion before. The parameter t will then be something like, e to the minus n. And CFT constraints are therefore not known to be satisfied to a precision of order e to the minus n. So when we say the crossing is satisfied from a supergravity calculation, we have actually not assured ourselves that it's satisfied really to non-perturbative accuracy. And so we cannot actually say it's only approximately equal to 0 in that sense. Now, the approximate CFT data define, as I said, these islands in the bootland, like the landscape of the bootstrap constraints, and it frees up, therefore, a parameter space to average over. Now, if you average over this, which is, of course, what we want to go to, then that will give you something like non-factorization. So you get connected contributions to the spectral form factor and other observables. But, so that's nice. But the immediate question is, what is an appropriate measure for averaging? So that's what I want to talk about in the last part of my talk. But I do want to say slightly, well, was an interesting point that deserves more thought, I think, that approximate CFT are just a set of data. So yes, we have sort of characterized them a little bit, but one can ask questions like, do they even define a local quantum field theory, right? Because we haven't started out with any sort of principle that would define that. And we do know that if the constraints satisfy if the data satisfy the constraints exactly, we get a local CFT. But if they don't satisfy those constraints, do we even get a quantum field theory? That's something that's certainly worth thinking about, because it's also important, again, in terms of characterizing the members of our ensemble. So let me now talk about the measure and move on to this tensor model. So you see, because I want to be more specific now, let's talk about ensembles for random two-dimensional CFT. But many of the things that I'm saying actually are true also in higher dimensions. It's just that the specific form of the potential that I will derive can only be derived in the clean fashion that I'm doing it now for a two-dimensional CFT. Well, hopefully clean. So we will construct a CFT ensemble for two-dimensional CFT concretely. As I already pointed out, this will be a joint statistical model for the data of a two-dimensional CFT, which we can write as the conformal weights and holomorphic and anti-holomorphic weights H and H bar. And we think of them as the eigenvalues of a operator Lij. So this is like will be our random matrix. And theCijk are just, by definition, a random 3 tensor. Well, there are 3 tensor, and we want to think of it as a random object. So what we're going to construct, in fact, will be some tensor matrix model. And we will construct its potential by imposing the approximate bootstrap constraints. And now you will see how this works, okay? So let's see, okay, I do want to, you said I have a little bit more time, right?
Yes, of course, yes, please.
Yeah. So in order to define the measure, we can, well, I was thinking of maybe skipping point A, but let me not skip it. So in order to define the measure, one can either consider moments of this ensemble and try to, deduce from moments terms in the potential. That's kind of intuitive, but not as, let's say, direct as method B will be, which is to use CFT constraints more directly. So let me just say a few words about A, but mostly focus on B. So this is actually the exact generalization of the statement I made previously about out-of-time order correlators and crossing invariant 4-point functions for these ETH matrix models. So let's suppose that crossing in the ensemble is satisfied on average, meaning you write the crossing equation, but you don't write the crossing equation for one particular element, you actually average over the entire ensemble. So then even if the ensemble is Gaussian, you start with a Gaussian ensemble, you can satisfy yourself that the crossing invariance is satisfied on average. And I should actually have cited here, this is, for example, what is done in this paper by Scott Collier, by Chandra and Tom Hartman and Alex Maloney. Okay. Now let's assume that the crossing equation is satisfied on average. In other words, statistically speaking, the mean of crossing over the ensemble is 0. Note again, by the way, this doesn't mean that every member of the ensemble satisfies crossing. It's just that the mean is 0. Okay. Now, in order to know more about what every member of this ensemble does, and remember that for consistency, we needed to specify that the violation of crossing should be bounded by this T parameter. So let's look at the variance of crossing. It should be approximately 0. And here by approximately 0, this is like, up to the tolerance parameter. Well, the equation that you need to consider then is you take, for example, a 4-point function of some external operators in the set that you're allowed to consider in the S channel, minus that in the T channel, squared, and then averaged over the ensemble. So of course, pictorially, this is S channel minus T channel squared in the ensemble is approximately equal to 0. Now, if you write out this equation, you will find that in the Gaussian model, again, this is arbitrarily violated. So the violation here is not uniformly bounded by a parameter that we call T, it's just arbitrarily bad. You can, however, introduce a quartic moment like we did before for the O's, which cures this and allows you to uniformly bound it. And the particular quartic moment that you need to introduce is determined entirely by conformal considerations. And in fact, because we're in a 2D CFT, we now have Virasoro. And it turns out, as we computed, that the connected contribution of 4 C's has to be given exactly by a beautiful group theoretic object in Virasoro called the 6J symbol, the crossing kernel. So this is a special function if you want. It goes back to people like Teschner and Moore and Seiberg and so on. So this is like, it's related to the fusion of 3 representations. So it depends on these 6 operators. And that fixes, if you want, the second moment. So remember, I said you can consider moments, for example, of the crossing equation. I now consider the second moment, and I found that I can satisfy the constraints approximately in the way I want by introducing this particular quartic moment. Fixes the second moment, but you might ask, what about higher moments? Well, you could keep going and you could try and determine what the higher moments are. But in fact, that would become very tedious. In some sense, a more efficient way, I don't want to say a better way, is by imposing these constraints in a smarter way. But let's just take away from this 2 things. First, because the mean of crossing is 0, doesn't mean that crossing, for a typical member of the ensemble is almost satisfied. For this, you also need to look at higher moments. The first higher moment that you look at, the variance, tells you that a Gaussian model will be inconsistent and you need to correct it at least by this quartic moment. Now you could go and determine moment by moment the distribution of OPE coefficients. Okay, right. Now, fixing all moments actually can be done in one fell swoop if you want, by instead thinking directly about the statistics of the crossing equation. And maybe I will try to explain this carefully. This will be the last thing I explain technically, and then I can give some summary and outlook. So technically speaking, what we're doing is that we're approximately implementing what's known as the Moore-Seiberg construction. But let me actually just explain what I mean by this as I go on. So what we do is we have a 2D CFT, and what we will impose is we want to impose the crossing equation on the sphere of 4 operators, again, up to the tolerance. And we want to also implement modular crossing of 1-point functions on the torus. And if both of these conditions are met, you have a consistent CFT. Now, we only statistically implement these conditions, and that means that we will write an ensemble of OPE coefficients C and of operators, which I'm here labeling by P, which statistically satisfy moment by moment these conditions. So for example, let us think about ST channel crossing on the sphere. I can write ST channel crossing on the sphere, which would have been previously that this correlation function evaluated in the S channel is equal to the correlation function evaluated in the T channel. Okay, I can abstract this away from the operators, and I can write it only in terms of the OPE coefficients. Okay, I'm summing over the intermediate operators Q, and I1, I2, I3, I4 label the external operators O1, O2, O3, O4. This would be the S channel. And I can write the T channel as I1, I4, I2, I3 with this fusion kernel of Tensor and Teschner. So this fusion kernel is the thing that allows me to strip away the conformal blocks if you want. So under conditions that we explain in our paper, you can think of this as being a local form of the crossing equation. So this is like the crossing equation. But how do you define now? Yeah.
Ask this F, you don't have usually a closed formula for F in terms of the C's, right?
F doesn't depend on these. F depends only on the external operators and on the Q and P. So the S and T channel exchanged operator. F is known in closed form.
Theory dependent. It is depends on the theory.
No.
F also it depends on.
No, it does not. The Tensor-Teschner kernel does not depend on the theory. No, it is a property of Virasoro. That is actually important here. Maybe we're not talking about the same object. I am.
Okay, I see.
It's not a conformal block. I don't know what F are you talking about?
No, sorry. This is the fusion kernel. I see. This is the fusion.
This is the fusion kernel.
Yeah. Okay. So this indeed should not depend on the theory. Okay.
And it does not.
Yeah.
But so now, this is the crossing equation. But I want you now to think of this equation as being an equation which equates something equal to 0, but has 4 open indices, namely the 4 external operators, I1, I2, I3, I4. So just think of this equation as being an equation that depends on the 4 external operators, I1, I2, I3, I4. I'm just rewriting this equation. And as a remark, I could also write modular crossing of torus one-point functions in a similar way, and it gives even a simpler condition. But now the total potential for C's and H's, these P's here are just some way of writing the H's, by the way. This is something that I'm not happy about, but it turns out that when you actually go down to write equations, it is much, much more convenient to use what people call Liouville notation. So the conformal weights H and H bar are now written in terms of so-called Liouville parameters P and P bar. It's just a change of labeling. I apologize for this, but honestly, all of the literature that determines these fusion kernels, for example, uses this notation, and it would be horrendous to do it in the H notation. Anyway, so think of these as H's.
I want to understand your claim. So you say that if you make sure, if whatever averaging procedure you implement, make sure that this crossing symmetry is respected on the sphere, and this modular constraint is modular crossing of one-point function on the torus source, then it is
these conditions together, if they're exactly imposed, would define consistent correlation functions on any genus Riemann surface with any number of external operator insertions.
Any number. So that's the claim. This is sufficient. But how to see that? Is it obvious? Because averaging, when you average this.
No. Sorry, Ian. In the average sense, there is no claim. We are the first to do an averaged version of this. Moore and Seiberg basically constructed rational CFTs this way, but specific rational CFTs. What we're doing here is a proposal for writing the potential for a tensor matrix model that describes an ensemble of CFTs. Okay.
Okay. So your claim is that once if you say that on the average these two are satisfied, then this averaging procedure would be consistent in arbitrary high genus. And is there a proof of it, or it's so far? I mean, up to some tolerance.
There is no proof, but I think when you see the model that we have, you will maybe understand a little bit more what the spirit is, and then we can consider what you might want to prove or not. Okay. I mean, because we're not saying that we're going to get one CFT, right? Remember, we don't actually claim that we get a unique CFT. We just average over approximate CFTs. It's a different thing. So the potential that we get is defined as the maximum ignorance ensemble of CFT data that imposes these constraints on average. So this and the modular crossing. And if you have no constraints of this kind, you get the Gaussian ensemble. You know, the maximum ignorance ensemble is just the Gaussian ensemble. Okay? But we're not going to get the Gaussian ensemble because we're putting in more information. So what is the ensemble that we get? Well, we then again get some ETH type tensor model where we average so H here is averaging over L and L0 bar. So the matrices whose eigenvalues are P and P bar. And we average over the operator product coefficient C, okay, with a potential. And determine the potential that corresponds to imposing this on average is the following term. It's a quartic term in V's. It's basically just the square summed over all external indices of this equation, okay? And what it gives you is a term which is quartic in the C's because it's the square of a term that's quadratic in C's, okay? It has some functions. Rho 0 of P is the Cardy density of states. C0 is the so-called DOZZ formula. So these are just known functions. Basically, think of them as special functions. I have my operator product coefficients in particular constructions here. Okay, I have basically the unit here. And I have a second term, which is governed by, again, the Virasoro 6J symbol. And why the Virasoro 6J symbol? Because the holomorphic square of this F function is actually the Virasoro 6J symbol. So this is how 6J of Virasoro comes. Now, there are more terms in this potential which come from modular crossing. They basically fix rho and its statistics. But the one that is most sort of evocative is this one that I'm writing here, because it is known that the Virasoro 6J symbol is actually associated with tetrahedra. So you now think of the edges as being related to the Virasoro representations that are carried here. So I1 is one edge, I2 is another edge, P is a third edge, I3, I4, P. And you can show that geometrically, this has the symmetry of a tetrahedron. So I didn't label the edges here, but you could label them in any way that is invariant under the permutations of the tetrahedron. So what this gives you is actually, it gives you a model. Let me just say it out. It gives you a model whose graphs are going to be given by vertices that are given by tetrahedra. So these, faces are triangles. The vertices are weighted by the 6J symbol of Virasoro. And you can actually find a propagator that glues triangles of different vertices together, which I'm not writing out here, but is exactly the same propagator that would have been written down if we had taken the Gaussian model of Collier, Chandra, Hartmann, and Maloney as sort of the Gaussian approximation of our model, right? The Gaussian approximation gives you the propagator. We actually get the same propagator. In other words, at the Gaussian level, we get the same model. So then, what the diagrams of the tensor sector of this theory are, is basically triangularizations of random three-dimensional Euclidean manifolds, where I'm weighting the vertices of the triangulation by the 6J symbol, and the propagator is given by the DOZZ formula. Okay, and so in that sense, this is a discrete version of three-dimensional gravity in the sense that the matrix that I introduced in the beginning was a discrete version of two-dimensional gravity. So this is what I'm saying here. So this two-dimensional random CFT basically gives a simplicial decomposition where the most evocative terms, there are other terms which I didn't write for you, are this triangle, and here I've labeled the edges, which is weighted by the 6J symbol times this known function of the DOZZ formula. And the propagator that glues triangles is given by this C0 function. This is, by the way, just a ratio of gamma functions. It's just some special function. And the idea would be to now try and take a continuum limit of this random CFT. And the conjecture would be that that gives you a continuum definition of three-dimensional gravity. but it's a conjecture because it's ongoing work. We have gone to some way there by basically studying the Schwinger-Dyson equations of 2- and 4-point equations and basically showing that they're consistent with what you would expect from ADS3 CFT2. But what it is the action itself is just manifestly a version of what people used to call simplicial gravity in 3 dimensions. And what I mean here is this literature, pioneered by Bulatov, Gross, and Ambjörn, and other people. So this is a version of simplicial gravity in 3D, with the exception that what we have here is actually governed by Virasoro, whereas previously people were thinking more about groups like SU2, Q-deformed SU2, and so on. Okay, so let me summarize here.
When you say that this is 3D gravity, you mean it is 3D gravity in some semi-classical expansion where e to the power minus s is now identified with, or
no, this is actually a discrete version of 3-dimensional gravity, because we have not shown how to take the continuum limit yet, right? So these matrices, if you remember, I started out with these matrices. Okay, so I said you zoom in here. I could say all these words because these people have actually worked out all the chains in the argument. What we have is the right-hand side here, where I integrate over a sort of a discrete tensor theory. Here, they're integrating over discrete matrix theory. And those diagrams give you discrete triangulations of 2-dimensional surfaces. An important ingredient for claiming that this is 2-dimensional gravity is the continuum limit. And the claim is that the continuum limit of these kind of constructions gives you a construction of the path integral on 2-dimensional universes. What we have done is we have started with the idea of a chaotic CFT, and we have actually just landed up on something that looks like the natural 3-dimensional generalization of the right-hand side of this. You see what I'm trying to say? There is like a discrete theory here, but which has a continuum limit that is 2D gravity. We have derived what looks like the most natural 3-dimensional generalization of this object, but from this averaging of a CFT's idea. Now, the next step would be to show that there exists a continuum limit, which this, for example, agrees with some theory of 3-dimensional gravity.
Okay, so unless you take the continuum gravity limit, you won't be able to say match it with some semi-classical computation in say ADS3 or.
Probably not. Probably not.
Okay.
Yes, probably not. So let me summarize. So we basically reinterpret these matrix type models as approximate ensembles of some Wiener type. We then, when we apply this to CFTs, we need to ask ourselves, how do we go ahead? I advertise these ETH matrix models as being sort of the mathematical framework that does it for us. Yes, there is some intriguing relation to what mathematicians call the theory of free probability, which would be very interesting to follow up on. And in fact, there is the group Korchan, Fouini, and Papalardi in Paris, who have been, pioneering also these non-Gaussian ideas, and they have recently written some very interesting papers in that direction. But they are interested just in the ETH aspect of things. Now we've applied this in gravity. I should have said that for the JT plus matter application that we did, we were able to take that step of the double scaling limit, just to be clear. So, in the JT plus matter context, we have shown how to do this double scaling limit, and how to do this in 3 dimensions is subject of ongoing work, but we are optimistic in the sense that we have previously implemented this procedure successfully, starting with this ETH matrix model for a gravitational model, and then defined a continuum limit. Now, low energy supergravity, basically some sort of moment generating gadget for our ensemble. Okay, it updates statistical information, and gravity would be sort of like the maximum entropy ensemble taking into account our constraints. The question is also, and what would happen if eventually you localize the potential so that the constraints become exact. would you land on a fixed UV theory, like one particular CFT, or what is actually going on here? And this, would be interesting to pursue in this context of recent discussions whether gravity really is an average or not. So let me actually stop here and thank you for your attention and take some questions. Thank you.
Thank you, Julian, for this really stimulating seminar. And so we can have a few questions now before you have to cut off. Okay, so not much audience left, unfortunately. So let me begin questioning. I have so your starting point is some kind of a mother CFT, and then you talk of consistent averaging around this, like freeing up this parameters. So in this way, you won't expect that typically you will get something like, you will probably get new kinds of gravitational theories in this way, right? And then it's
the starting point of a fixed CFT was just to give you one example of such an approximate CFT. In general, we think of these as independent constructions. We don't need to start with a mother theory.
Yeah.
It's just that I wanted to give one example, because if I just give you these definitions, if there is no actual example, I'm talking about the empty set. So I just wanted to convince, and also we wanted to convince ourselves that such objects actually exist. Okay, so in general, you don't need to start with a mother CFT. In fact, it's an interesting question, for example, whether in every of these islands that our approximate constraints allow, whether there is an actual CFT in there. It's not necessary from our construction, and not guaranteed. You see what I'm saying?
Yeah, I understand. Because you are just simply taking this more cyber type constraints and just
into
feeding it into and constructing an ensemble such that you're constructing a maximum entropy ensemble that satisfies these constraints.
Correct. So, and here I just wanted to give one example as a sanity check.
Yeah,
and we just found that we could construct such an example from this naive idea of deforming an actual CFT, which is natural, but it's not the only way that, we believe that's not the only way that such things exist. And of course, one of the strong reasons is this idea in holography, that anyway, if you calculate every observable that you can in supergravity, you haven't really fully satisfied to non-perturbative accuracy the CFT constraints. So all you can say is that you have a CFT up to non-perturbative corrections, potentially.
I see. But I'm still a little confused by this because, in principle, you could think of different kinds of ADS3 with different kind of compactifications and different gravitational theories with different.
Yeah.
So of course you say that I'm only looking at the light operators, and you still need to show that if you kind of select to only light operators, you still get something universal,
so I did not say something crucial, I think, in that aspect, which is that when I wrote this equation here, this actually involves, so this equation is actually really rather subtle, and we had to think about it carefully. Of course, in papers of Teschner and so on, this is all spelled out, but it takes some time to understand it. In order to be able to have a local crossing equation, like one where you really strip off the conformal blocks, you have to basically be able to invert the crossing equation. And this inversion involves some choice of contour. And it can only be done in this form if, at least as far as I understand, it can only be done if the operator content of your theory is the identity Virasoro block, and then the continuum of states above C-1/24. So precisely what we would expect to be the universal content of pure gravity. So there's gravity, then there is the black hole threshold, and then you average over all possible microstates above the threshold of C-1/24. And if that is your assumption on the spectrum, then this is the only, then you can write this equation as cleanly as this. If not, you actually have additional contributions, which then make the potential let's say, far more complicated and less attractive.
So
we have
you were
actually
saying
put
that
in
average
some-
can be performed only if
I
you
think
have this
average can still be
assumption.
performed, but the potential will not look like this Bulatov thing. It will have some correction, which I wouldn't know what to do with.
I see. Okay, so this is one kind of consistent averaging that you could.
Yeah,
That's
so it's
naturally.
particularly nice,
But still,
consistent averaging, and it's interestingly exactly related to the exact spectrum of what we would think should be semi-classical gravity. And this comes out from, as I said, detailed considerations about the inversion contour, if you think about this ST channel crossing.
I see, but this for this I have to read your paper. Then.
Yes, and also I should say papers by CRS, Maxfield, Collier, and also Maloney. So, you know, they worked this out, and I think wrote it in a way that is more approachable maybe than some of the Teschner papers, but it is also in all of the Teschner papers. Well, yes, it is. Yeah. And we describe it, so you can also read our paper. But yeah. Okay. Well, you seem to be the last one standing.
Thanks again for this. Thanks for the wonderful sentence again. So I stop the recording.
Yeah.